Okay, hi everyone. Welcome back to lecture 2. Today we'll be talking about, making our ability to understand the world with numbers better, and especially in terms of sizes, distances, lengths, in the global manner, in the microscopic manner, in all of those angles. And just to get us going, I remember I'm asking you all sorts of questions, both in the exercises and in class. I know some of the questions are pretty hard. So let's start with a more simple question so I get also to know a bit more. I was wondering about the background of the people here. So who's coming from, let's say, biology? Lots of people. Who's coming from chemistry? We have a few people. Who's coming from physics? Also 2 times few. Who's coming from, what did I forget? Computer science? Lots of people. Engineering? Some people. What did I forget? Other subjects? Social sciences? Education? Okay, we have a few of those. Great. Okay, so we also have some heterogeneity here, and it's fine. I'll remind you, even though we'll be using mathematics, I hope that all of you, it shouldn't be too demanding. Even though we'll be focusing a lot on biology, what I expect is to be able to just catch up whatever you need by just doing a bit of reading in Wikipedia or whatever is your sources of information you like, and other stuff on, let's say, sustainability, etc. I hope it's also things that you can catch up if you feel that you're not from that field. If there's something you feel becoming too much jargon, all sorts of things like that, just either ask me in class or write to us if you want. We have the email of the course, so just let us know. Good, that's one thing. The other thing is you already were grappling with the first exercise. Who got to hand it in already? Okay, the majority. Who felt it was a waste of their time this week? Okay, let's make it a bit more concrete just to understand, who did it in less than an hour? Who did it in an hour to 2 hours? 2 hours to 4 hours? More than 4 hours? Okay, so I know it's challenging on different, and it's different. I hope it was a useful time. If you feel that you were spending on it more time than made sense or something like that, also find a way to let us know. It could be anonymous, whatever, just so we'll know if there's ways to improve it. We'll be happy to try and improve. For next week, you'll see there's a new exercise waiting for you in the website. It will be, again, a bit of challenging, but I hope not too much. We don't have. No, okay. Sorry. So we have the exercise, but next week we don't have the lecture. Why? I don't remember. Okay. So we have another festivity in the year. So next week there's no lecture, and the next lecture would be in 2 weeks, which means that you'll have a bit more time to spend on doing the exercise. Okay, good. So we did a short survey and we're done with the exercises. Anybody has other comments or thoughts about dealing with the exercise, trying to solve the questions? Anything you learned from this? Okay, I talked to people before. You learned stuff, but it feels strange to say it in front of the class. So I respect that as well. Let's go back to the question we ended up last time, which was, what is heavier? Although I would say you could also think about it as bigger in some sense. An mRNA or the protein it codes for. So for those not coming from molecular biology background, proteins are the machines doing stuff in our bodies, and the mRNAs are just these short emails that are some messages that are read from the DNA, and the code give the blueprint to making the protein. So the options are the mRNA, B, the protein, C, the same, or D, It depends. And as you already understood, when I'm saying the same, it doesn't have to be the same. It could be, within, let's say, few-fold. Okay, let's make the survey once again. Who's voting for the mRNA? Okay, who's voting for the protein? Who's voting for the same? And who's voting for it depends? Good, so I already see that there's been some progress or difference from last time for one reason or another. But let's try to derive it ourselves. Okay? So what do we need to do? We need to think about mRNAs and proteins. Okay, anybody has a suggestion? Let's start with, what do you prefer? mRNA. So let's start with the protein, just to make it more interesting. Okay, so let's start with the protein. How do I derive anything about the weight of a protein?
What is the single unit?
Good, so kind of like in the divide and conquer, protein could be many different types, it could be complex, but let's start from the building block. Okay, so what's the building block of a protein?
Amino acids.
Amino acid, I remember that as well. Okay, good, so there's this thing called amino acids. So how much does an amino acid weigh? Maybe you remember, maybe you don't, maybe it depends.
It depends.
It depends. Okay, so even though it depends, we still want to get something, some handle into it. And the way to think about it is maybe the fact that if you already know the name amino acid, there's actually a lot of hints inside this. Okay, at least in the way I think about this thing, but I don't remember things, by heart so much. But there's amino and there's an acid. Okay, anybody remembers what is an amino and what is an acid? Okay, so there's something with all these C's, right? Okay, so let's say acid. So I don't remember exactly, but there's something with so there's a carbon, which is like in many things in biology. And then this carbon to be an acid, there's all sorts of things that maybe you learned it or not, something with an oxygen. Something like this, groups of oxygen, carboxylic acid, all sorts of names like that. So it's something along those lines. I don't remember exactly the details beyond that, but I think that's good enough for me for now. Amino, what does it mean? So there's something with N, NH2, so maybe there's another H here. Something else. So I remember like with carbons, you need to have like 4 bonds, right? So the 1, 2, 3. So maybe there's another one here. NH, so it needs to have 3 bonds, so good. You said H2. Let's write it differently. Let's make an H here and an H here, and I have another bond freely available. Okay, so I think I kind of like have a mapping of what could be an amino acid, so I can do the calculations from this. But it's kind of boring, right? Like, why is it like there's something missing still?
The residue.
Yeah, so there's this thing called the residue. Why do I need the residue? Yeah, so like if you want to make proteins out of this, it would be pretty boring because it's always the same. So there's like a catch here, which you can put the catch. Let's say if this needs to connect to here, then let's put the R. I don't remember. Where is the R sitting? There's another carbon. Yeah, good. Okay, so there's another thing here. Good, you remind me. And here you have some magical thing called R. I'm about right?
Another hydrogen.
What?
Another hydrogen.
Okay, so there's another hydrogen, but hydrogen are on the house, as they say. Hydrogen is just like one Dalton, You put hydrogen everywhere you want. Okay, so we have this. So now we have the acid, amino acid, and something which makes the magic of life. Every time it could be something different. And of course, this might have some weight. I don't know what. We'll get to it in a minute, okay? Now we want to get the weight of this amino acid. So how much would it be? 10 is good. Okay, so 10 to the what is the question. So let's try and make the calculation. I have the carbon here and the carbon here and the nitrogen here. So that's 10, 10, 10. Right? So I have like 30. I have the oxygen. Oxygen is 16. So let's make it 20. Okay, so 10, 20, 30, 40, 50, 60, 70. 100. I have something here. So I have 10 to the 2. 100 Dalton. Make sense? So of course there's like these R. Sometimes there's like some crazy ones, proline, or I don't remember which, like tryptophan. There might be some elaborate stuff, but also it's like a few things, so maybe it would be another 100. Maybe it would be like 200. Okay, I don't remember what's the biggest one. Maybe the surprise me and it's 250. If I remember correctly, it's something on the average, or maybe it's like 110, 120, like we're pretty good. Okay? Obviously, it depends, if my life depends on whether it's 100 or 200, I wouldn't be so laid back. But what we're doing is just like, we just want to answer some silly question that, just gives us some intuitions, but probably it's not like I don't need to know it to save my life to within 10%. Good. Let's go to the other side. So we solve this issue. mRNA. Okay, yeah, it's a bit surprising that, I was also surprised. It's 100, and now let's make it like this, Dalton. It looks a bit like 1,000 for a second, sorry. Okay, what do we do about the mRNA? Yeah, so let's try and do the same, although now it's a bit more complicated. It took time to Watson and Crick to solve it. And so what's in an mRNA? Yeah, so there's these nucleotides. So what do I know about this? So there's like a double helix, right? I wouldn't try to, but there's some backbone and there's something here connecting some other thing, and they meet each other, and this is like... What? Good. So this is DNA. Forget that I said it, don't tell everybody. And this is DNA, and we're doing mRNA. Okay? Good. My tenure was at risk for a second. I'm a professor of biochemistry, so I shouldn't... Okay, so how does this whole thing happen? I now really don't remember much about it, but there is... how does it go? What do we have here?
Sugar.
There's a sugar. Okay, sugar, you know what sugar looks like? There's somewhere here that looks like this, right? Roughly? And these are carbons. Okay, so we have a sugar. What else? Phosphate. Phosphate is here, right? Good, so we have a phosphate here. Let's say it's connected or something like that. What else? The base. Okay, the base is here.
The ribose is also on the backbone.
Right. Good, you remind me, it's good. Okay, we're going back from the beginning. So there's something like this, right? It's like something like this now, and with the phosphate somewhere here. These are the carbons. And now this connects to another something. Something like this. Because this needs to connect, like in DNA, it connects to something. Right, and I have the phosphate now connecting to another one of those sugars, etc. About right? So. Okay. Okay, so let's now try to estimate what's the mass of this thing, unless I forgot something really big.
Is it 6 or 5 carbons?
Yes. Is it 6 or 5?
5.
5. Okay, so I'm used to thinking about like glucose and stuff like that, but you're right, this is a pentoses. So I don't want to, redraw it. Believe me, like I believe you, it's 5. So it goes like this. Okay. What? I think we're done. Okay, so what's the mass? Like, how do we do mass from here?
10
Okay, 10, 50. Phosphate is heavy.
Phosphate counts with oxygen.
What? Yes, there's also, right, good, that's important. This phosphate, it has all sorts of oxygens here. Something like this, right?
More.
What?
One more.
One more?
Between the phosphate and the carbon.
Okay, this is now becoming a disgrace. Let's do it again. Okay, so like it was mRNA version 1.0, 2.0. Now we're doing 3.0. The ultimate mRNA. Now we know it's a 5-carbon sugar. And we have here oxygen going to phosphate, going to oxygen, going to oxygen, going to oxygen. I don't know how they connect somehow. And now we have this connecting to something. And now it repeats itself. Okay, so we have 10, 20, 30, 40, 50. Okay? This is another 20, 20, 20. It's 80 together with 130. Let's say 160. And now there's all sorts of stuff happening here.
And then you also have
What?
You also have 3 of them for each amino acid.
Yeah, so we'll get to that in a minute. But here we got like 200, 300. So that's like a few times 100. Okay, you remember this F or few? You can think about it as like 3. So we have about few times 100. Okay, and now there's this other point, which is okay, this beautiful code of life in which it's not like this gives you this, but this codes for something that together with other things tells you which amino acid you should put in, right? There's like 4 types of this. And naturally, there's 20 types of this. So clearly, you can't from this know this. But if you have 3 of this, the combinatorics gives you 4 times 4 times 4, 64 options. So with 64 options, now you can, information theory enables you to do the correspondence. And indeed, we need to multiply this by 3, which brings us to about 1,000. Okay, so what we see is that the building block of an mRNA is 10 times bigger than the building block of a protein. Yes?
Also, you have usually the non-coding.
Great, so let's get to it in a second, okay? So just 1 second. So already from this, like, the most, simplified manner, once you put it together, you see that actually it's very different, and it's by far the protein. The mRNA, of course. Good. So the mRNA would be much heavier. Not only that, but there's also another layer of stuff, which is, yeah, so nature did it in an interesting way that, like, it's not, in this mRNA, you have all sorts of other stuff, or not, more, and that would just make things worse, right, in terms of the relationship. The mRNA would be even heavier in that respect. Okay, so this means that this is the answer. And even though it's easy for us to go for it depends, it actually does not depend. This is the answer.
How do we know that the number of building blocks is equivalent between we saw that each building block is like the mRNA is bigger when you look at specific. What makes us think that they're...
Okay, so 50 years of molecular biology or whatever, like they understood this thing called the central dogma, which was elegantly presented by Crick, that shows that, like, for each such 3 letters, you're getting 1 letter from here. Or for 3 building blocks, you're getting 1 building block. And sometimes it's a bit more complicated. You could have more, but this gives you, like, the stoichiometric ratio. But maybe you asked something else. Was this what you asked, or as like an...
I could imagine a situation that you have 1 codon on the mRNA, right?
Right, codon.
And it builds a protein with 10 of this. It says, okay, this is the building block that I want, but I want 10 of them. But okay, it's not the situation.
So I think you're inventing like a new paradigm for, let's say, in synthetic biology. Maybe you'll find it could have been nice. In computer science, you do such tricks of, like, special codes that you say, okay, now I'm doing this is what you need to do, and now do it 10 times.
Yeah.
Okay, for that you'll also need to invent like a new ribosome that instead of currently just doing that, you'll have to say, okay, now I need to read how many times to do this, and I think you can make quite a career if you're able to achieve it.
From a single mRNA, you can produce multiple proteins, right?
Right.
That's not the question.
Okay, so there's a different. So actually, this also brings a point. So per in the comparison I did between mRNA and the protein, mRNA are way heavier. But you can ask a different question, like say, in the whole cell, what weighs more, mRNAs or proteins? And then it might not be the same answer. Why? Because exactly the point raised here, that for every mRNA, you might be getting an amplification, many copies. Okay, but I'm still curious about what you suggested, find some good synthetic biologist and, maybe you can make something big. Okay, is that surprising? So there's something a bit strange, right? Like it seems that if I remember correctly, last time I was asking you this question about like kind of like your gut feeling before you had a week to do exercises and see if you had some tricks in the course. The majority were voting for the protein. I would also say that's kind of like, I've been running this for quite a few years now. This is the gut feeling of most people, or let's say people who knows, you would ask and would give you an answer. How come?
You see the structure, you see the working structures all the time with these fancy maps, but you never really see the mRNA, like what it looks like in 3D space, or you never see them side by side for sure.
Yeah, so proteins are more of like, the poster child of molecular biology. You see them a lot. Okay, so that's one thing, yeah?
So most of the time when you study stuff that build other stuff, the building blocks are smaller in the world.
Yeah. And energy is put into the process of making the protein, so you expect the product like to have the additional energy that was put into the process of making it, which could increase its mass or weight.
Also, the way we talk about RNA is that it's like the code, like computers, which doesn't feel like it has a mass. And
Okay.
Proteins.
So there's something that I think combines all of these things. So let me repeat that for a second. I think like we're bringing into the discussion or into our thinking all sorts of notions from our normal life, right? We're thinking about, say, building blocks and what is created, and the building blocks are small and what is created is big. Or that when you're doing coding, you start with something small and you create something big. Or let's say if it's construction, you have blueprints. The blueprints of the villa that somebody builds, the blueprints are small and handheld, and the villa is large. Okay, so many of those things. So I think it's interesting to reflect on that for a second, because I think that happens to us a lot if we are aware of it or not. We're studying here things that are molecular. We never met them, and we don't have a good intuition for them at all. But we tend to apply the kind of intuition we have from normal life about them, and that sometimes, is useful because we need some intuition, but sometimes it can also lead us completely wrong. And for that, numbers give us this extra sense to try and understand things that we don't have an intuitive feeling for, and with time you can build it further. Good. Yeah?
So just occurred to me, but without being annoying, that you could potentially see a case where you have an RNA that goes for a subunit that creates a protein that's much larger, like a dimer, whatever, something that's much larger than the actual RNA that coded for it eventually.
Okay, so that relates to another thing. We might be talking about it later. There's this thing called oligomerization, where you could have a protein meeting with other proteins which are exactly the same, so they were coded by the same mRNA, and now building this huge structure that might be bigger than the mRNA. That's what you had in mind? Yeah, so you're right. That's another layer of things that could happen.
In most cases.
Just 1 second. What?
What about the mRNA that codes to mRNA?
mRNA that codes for an mRNA? That's something new? I don't know. Okay, maybe we could talk about it. Maybe there's also something interesting here.
For what you said earlier, I think in most cases that I know, it doesn't come to 10 units the same protein, so still 110 times will be less than 10 times will be still smaller than 1,000.
Okay, so I think maybe that would be in the next lecture. We'll be talking about concentrations. We'll be talking about how many copies on average from each mRNA turn into a protein. So I think that would be a great time to...
The same unit of protein makes one bigger protein.
In terms of oligomerization. Yeah. Good, okay. So it's true, usually you are right and you'll have less and then it doesn't. But in some cases it is true and they would be bigger, and we might be seeing examples later on. Okay, any more, let's say this was good, that was about the relationship between, what makes us, think about correctly or not. Anything of biological insight that comes out of it? That comes to mind? Now that you understood it, like mRNA is way heavier than the protein, let's say 10 times or actually even more if it's non-coding, does it have any functional implications? Dina?
We looked last week about the number of proteins in the cell, but actually we assume that the 30% that's not water is all proteins, but actually the mRNA is going to take up more space than the protein, so it's going to be off.
Okay, so you're saying we might need to revisit our thinking, how dominant we think about proteins, how dominant are they in the overall weight of the cell? Okay, that's one functional implication. Yep.
There are some like remote translation. We know on something it's much more expensive than local or something. It depends like where and how this translation happens.
Okay, so let's take an example, or let's follow up on what you're suggesting. In neurons, which are pretty big, you need to transport stuff. And usually you have an option, or like you need something at the end. You could either transport the mRNA or you can transport a protein. Right? What would you transport?
Protein.
Yeah.
It depends.
What? Yeah, so now let's say it raises the question of, okay, what is better, to transport this or that? And there's also a question of, okay, how many copies are you going to get? Like maybe if I'm moving one mRNA, I can make a lot. But now it puts it on a much more concrete, quantitative angle to this question. What is better and why, etc. Okay, and that relates also to diffusion. You know, things diffuse inside the cell. If you're heavier, you're diffusing more slowly. That's a big issue. And now this tells you something about what would diffuse faster. I didn't ask you that before, but I'm not sure that you would have known. What would have been diffusing faster? Again, our intuition would say the message is easier to transport than the cargo that's being built of it. But actually, it's the reverse. There's also this thing about evolution, right? What happened in evolution?
First where the RNA was like functional, we think. And
Yeah.
then I like to imagine it like, it's like the RNA is like big Legos and protein is small Legos. So with small Legos you can build much more fine machinery.
Right, so in evolution, the current, let's say, paradigm, although there are some other suggestions, is that there's an RNA world, that's how it all started. And from there it evolved into the protein world that we know today. And when think about it now, it actually makes sense in many ways, right? It's kind of like the miniaturization in electronics, that you make things smaller and smaller, and by that you make them more efficient and all sorts of other stuff. So it seems like here's an analogy, it's actually similar in what happened in our world, and like it moved from bigger parts into smaller parts. That's usually more efficient, more ta-ta-ta-ta-ti-ta-tam. Okay, and we could talk much more about it, make some speculations, but I think you got the point. Okay, so I would say, it gives us all sorts of functional implications in different ways. Any more thoughts before we move on? Take your time if you have more suggestions.
I think there's also maybe a question of if we have problems with that machinery, if they're so drastically different in size and weight, where is that problem going to be? Or you're going to have different problems, because technically in the mRNA you have more space for there to be problems, more elements, more things that can get messed up. But in the protein, things are a lot like the same information is a lot more compact, and so sort of a tiny change in there might have a much bigger impact on the protein than a tiny change in the mRNA. So I think that's also something to think about.
Great. So I could take it further and say, like, now you understand that mRNA is a much bigger machinery. So there's lots of more other stuff as well, like in terms of like things that could go wrong in different ways, but also maybe if you want to put on some, I don't know, different tags, or you want to interact with it, because in the end everything happens through molecular interactions. It's something much bigger to interact with in many ways. And we should be aware of it. Maybe nature's found a solution and it could do all the interactions also among proteins. But with mRNA, you have way more space to do it. So that's another way to think about, like, in terms of like functional implications. You might also think about, say, the ribosome, right? How is the ribosome? It's like this combination of mRNA and protein. And again, in the understanding of the RNA world, it moved from being mostly like only mRNA, and it transitioned into replacing some parts with proteins, which is kind of elegant. Like you throw away something like really big, and you're putting some other stuff which is more agile and small, etc. Yeah.
Just she reminded me of something. So what argues a bit against it? So in the medicine now, so RNA therapy is like this is something that the world is going to, and it all focuses on the RNA metabolism against COVID or whatever. now cancer therapy.
Okay,
They are focusing on the RNA as the main hub of the problem.
Okay, so of course this doesn't capture everything, right? Like I'm not saying that like from this you understand everything that happens today in medicine, in evolution, in life. It's just I was just wanting to show how it gives you another angle to think about problems. I would say that to your point exactly, we'll talk more about concentrations in the next lecture. I think this thing about the amplification that was mentioned before, like how many copies of protein you get per mRNA, maybe that will also give us some insight into why is it better in some sense to have the drugs that way and also other things. I have lots of other stuff I want to tell you today. Okay, let's move forward or sideways, and let's give you another question here. What is the number of atoms in your body? Question is clear? Simple question. Okay, so I want every person to try and just come up with an answer before. I don't want to have people affect other people. So try to come up for a second with a suggestion, and I'll collect them in a second. Okay, we're open to business. So let's get a lot of numbers. What do you say? Okay, just throw, just.
So.
No, just number. Like, just give a number, it will make the.
10 to the.
I just want to get lots of answers, and you'll see what I'll do with it. Okay, trust in me for a second.
10 to the 30.
10 to the 30. So I have 10 to the 30. 10 to the 30. 10 to the 27.
40.
10 to the 40. 10 to 100. Yeah, just give me lots of answers. 10 to the 29. 10 to the 20.
10 to 25.
10 to the 25. We don't have a no, we just have a yes now. It's a 10 to the 19. 34. There's more people here, so just give me some more options. 10 to the 15. 10 to the 10. 10 to the 60. Okay, I think we're closing the bet. Okay. So now look at something okay, first of all, it seems like you don't know the answer. Okay, that's fine, and there's actually quite a lot of diversity, which we're happy about, so that's also good. What do we do next?
Average.
Okay, let's take the average. So just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we need to do this plus, okay, so we need to do this plus this. Plus this, just 1 second.
The average is about 10 to the 30.
Give me a chance. I'm here for a good reason. Okay, so I can just add. I add all of these together. Sigma of xi, and I divide by 12. Okay. What would be the answer? 10 to the 100. Actually, it will be 10 to the 99. So thanks to I don't know who gave this. Very good. You gave me a great example. So you'd get 10 to the 100. Okay. This is the way we're doing averaging. That's the way we get, responses from everybody. That's one way to do it. Is there another way to do it? Okay, average the exponents. Any other suggestion? Okay, so let's get to that in a second. So there's like the suggestion here, take the average of the exponents, or I had other people saying take the geometric mean, which is nice because it's the same thing. Okay, what does that mean? Geometric mean means, so if I have, somebody says, if somebody says, x1, and somebody says x2, and somebody says x3, you just multiply them. X times x, no. x2, x3, whatever, and then you take the root. Not a good example. Again, let's do it again. Somebody says x1 and somebody says x2. I could just take the multiplication of these two and take the root. Okay, and we could repeat it if it's 4 numbers, the 4th root. Okay, you can do the math. It's exactly like taking the average of the exponents. Why? Let's take an example. Let's say somebody says 1 and somebody says 100. The usual mean would be like 50, right? Or let's make it more interesting. Let's say 10,000. Okay? So the average of that is really pretty close to 10,000. It's like 5,000. But if I'm doing this geometric mean, it's 1 times 10,000, which is 10,000. Square root of 10,000, that's 100. Equal now. That's 100. Which is 10 to the 2. Which, lo and behold, this is 10 to the 0. And this is 10 to the 4. So 0 plus 4 divided by 2 is 10 to the 2. Okay, so it's kind of, what?
It's much more obvious if you show the square root as the power of half. And you're exactly showing that
You're right. Good. So let's do it. Let's do it
the power of 1 by half.
Okay, so let's call it, this is 10 to the y1 and 10 to the y2. And now I'm doing this times this, 1/2. And then it's exactly like 1y plus 1y2 divided by 2, and then it comes out. Okay, another way to look at it. If you're not into these math tricks, that's also fine. Yeah, it's like, I think you got the idea. Okay, how does this brings us to this concrete thing? So we had this as one option. The other option was to try, anybody has a computer here? That's like, on the phone. I need to do 30, okay, let's do it. This is 57, 97, 197, 126. I'm getting, it's too much for me. 186. Somebody can do just the average of the exponents for a second. So basically, there's a notation called pi xi, and then to the 1 over 12, and this comes up to 10, 34. Good. Okay, so now we have another suggestion. And there was another idea here to take the median. You remember what the median is? It means let's order these according to like from top to bottom, and let's find the middle one, and let's see what it amounts to. Okay, so anybody could tell me? Let's do it. How do we do this?
Let's. The 29.
No,
the 27.
Okay, let's throw the biggest one and the smallest one, and then the second biggest one, and then the second smallest one, and then what is this one and this one, and maybe also this one, and this one, and now this one and this one. I'm left with these two. So I came up with, let's say, the average of these two, 10 to the 28. That's the median.
Which average?
Whatever. Between 27 and 29, like among friends, it's like. Okay, so the idea is clear? Good. Now let's try and do the calculation. So now this was like, we threw some numbers, we got something. Let's try and do a more proper calculation. Let's say we have more than a few seconds to work on it on the back of the envelope. So I'm asking you, how would you approach this question? Think for a second, if you really had now, I gave you 10 minutes to do this. How would you approach this? No, just everybody to think for a second. Like, you see what I mean? I'm saying, like, let's say now we took like 10 minutes. We gave you that challenge. You don't have to give me the answer, but just the method. What would be the method in order to do that?
Divide into building blocks, like in the mRNA. So the body is built out of tissues, out of cells. Cells has molecules generate.
Okay, so we could try and do this top-down analysis, and actually we'll be doing something similar that Ron would show that he did, in his PhD, and there's cool stuff that could come out of it. Any other strategy for now? Yes?
You could think of just the weights, so how heavy is the body, and then let's say, okay, we're mostly organic materials, so most of the things are going to be carbon, oxygen, nitrogen, nitrogen. Find an average weight and just divide.
Good. Any other suggestion?
Yeah.
Yes?
I would actually take, like, assume we are water, and maybe after this we will calculate the organic stuff.
Okay, so you're taking the water human, or whatever, aqua human. I like it, and I think it connects also to what you were suggesting. Good, so let's try and do it together. What's the weight that we should take?
200.
Okay, so we need to take the weight of a person and divide it by the weight of a molecule or an atom. Yeah. Good, I'm getting there in a second. Okay, so a weight of a person.
90?
Yeah, so I think 10 to the 2 kilograms would work well. And now a weight of an atom. Yeah, so 10 Dalton, right? Because we could think about, for example, water as a good, or we could talk about organic stuff in a second. So what do we have here? This is, in terms of molecular weight, this is 16 Dalton. This is 1, and again 1. So average of this, about 10. Okay, if I needed to put, but let's say we were, you dehydrated me, okay, which might happen, with climate change, it might happen, unfortunately, at some point. So alternatively, we could do just organic matter. How would you write it for organic matter? What would be the formula for a human? C, that's good, I like it. C, very elegant. So are we only carbon?
No,
Like to a first, what does phosphate? Just a little bit. Well, okay, what would be the next thing after carbon, except for phosphate? Okay, there will be hydrogen and oxygen. Okay, so let's try to make it into like a molecule. I want to make a human molecule. So I had H2O is like the first order. Now I want to add to this thing, just extra something. So I'm adding hydrogen, I'm adding oxygen. What else? So I can add nitrogen, but actually I think it makes more, it's more like another hydrogen. I think like in terms of stoichiometry, it would be kind of like this. Although in some cases you put some nitrogen. Anyway, so, and then if you look at the weight of this 16, 12, 1, and 1, what's the average? Again, it's 10. So, okay, so we have 10, and what is it? 10 Dalton. Okay, what do I get from this? Again, I got 10. Crazy what's happening here. But what is this 10? So somebody wants to say Avogadro, right? Something with Avogadro. But is it Avogadro? Yeah, so this thing with this Avogadro, it all works with grams. I'm sorry. They didn't work with MKS, like with the normal, like with the right unit, standard, but they're working with grams. So I'm sorry, I forgot, but we have to change it for a second. I hope it's still not too much work for you to follow. We have to change this from 10 to the 2 kilograms to 10 to the 2 times 10 to the 3 grams per kilogram. This is kilograms. And then divided by 10 Dalton. So I have 10 to the 5 grams in each one of us, divided by 10 Dalton, which gives us 10 to the 4, what? Moles. Okay, maybe you remember, maybe you don't. Mole is like this Avogadro number of atoms. Okay? And something that weighs 10 Dalton, like something that has a molecular weight of 10 Daltons, if you have 10 grams of it, it would be 1 mole. Okay, you can brush it if you forgot all about it. Okay, so now I have 10 to the 4 moles in every person. How much is a mole? Okay, 6 point blah, 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 blah. But the important thing is 10 to the something, right? 10 to the 23, but 6 times 10 is like 10 to the 24, which is kind of like what? So this means that we have about 10 to the 4 times 10 to the 24, so about 10 to the 28 atoms.
In a single human. What about mass?
Median works pretty well. I like it. It's actually pretty interesting. You know, when you ask, so we're dealing with these statistical methods a lot, and we really like doing the geometric mean, but we also have more advanced stuff, whatever. But then when you talk with statisticians, when I try to talk with them about it, they always say, take the median. Why like take the median? So it's nice. So it's nice, I think, like both that you see can work with the median, but also if you think about it, with the geometric mean, we were about 60 orders of magnitude better than if we took the average. So it's actually pretty useful. You can close the door at least. Or if somebody could find the person doing the noise and could make them stop it, I will also be appreciative. Yeah, close the door in the meantime.
But I think it depends who gets first, because it's only bounded us around 10 to 30. If someone had said 10 to 200, we could have gone more in that direction.
Okay.
For me, anyway, I saw 10 to 30, so you guess plus minus 5, 10.
Okay, so Dina suggests that actually there's also like an anchoring effect, that the first person that said 10 to the 30 was so like, you know, affecting the other people. Maybe true, maybe not. I don't know. I'm sure there is some effect to that, although I did try explicitly to ask you to make your mind independently of other people. But I would say I've been repeating this, you know, every year, and this kind of like magic seems to work. Okay? It's pretty consistent there. So maybe everybody has some anchor. Anyway, I think it works pretty nicely. I'll give you some more examples in the future.
In previous years, was the median also better than the geometric average?
So you know what? In most years, I was just making the contrast between the arithmetic mean, the regular one, and the geometric mean. This thing of the median, I think, is like a new invention.
I think like you could have enough types of averages, and one of them will have to hit the right one for every type of.
That's an interesting proposition. So let's see what's your name?
Ori.
So what is Ori suggesting? He says, actually, there's enough ways to come up with averages that one of them would be okay, right? Yeah, so I could do many tricks, but I would say actually you'll have to be pretty creative in the way you make averages, so that if I have 10 to the 100 options, I'll be able to, you know, I need a lot of types of averages. No, anyway, I'm just joking. It's also a valid point. There could be like a multiple hypothesis, but I'm actually, you know, I'm really between 2 options or 3 options. Okay, yeah.
So there's a deep reason for the geometrical kind to work, right? I don't know to explain it, but it has some reason to work.
Good. So you have some intuition that it's not really magic. There's like some underlying mechanism here, but it's not really easy to put your finger on it. So I agree with you, and also for me it's not always easy. There are other people that dealt with that problem. I think very often it relates to the fact that our cognition is actually in logarithmic scale. Okay, there's a way to do all sorts of nice experiments about it. Maybe you remember a nicer example. I remember, for example, that they tell you, okay, close your eyes. I give you 2 different weights to hold, and they ask you, let me know when they're different. Okay, and it turns out it's called whatever. It's in psychophysics and stuff like that. You don't tell differences of like 10 grams. You know differences of like a factor.
Same
okay.
as for sound. That's why we have decibels.
Exactly. So with sound, so this is about weight, but it's also true for sound. That's why the level, or like the level are in decibels, which are anyway. It's also logarithmic scale. It's also true for our eyesight. What are the units? I don't know if they're giving. Yeah, but that is a linear scale. But people know that like also you can tell differences also in fold change, and there's lots of other stuff. So anyone here from cognition studies or something like that probably could give more examples. So this might be one reason why it's that way, but it could be all sorts of other reasons. There's properties of things like when you multiply things, it tends to be logarithmically distributed, whereas when you add things, but many things happen in this multiplicative thing, because if you think about, say, the central dogma, you have a DNA, you're making a few mRNAs. For each mRNA, you're making a few proteins. So there's also this multiplication happening along the way, and things like that. Any more comments or thoughts about this? Okay, I really love the geometric mean, and I will learn to love the median as well, but I think you'll find it's pretty useful in different ways. Good. So we're here, we did this. Let's talk about this for a second, or more than a second, then maybe we'll take a short recess. Okay, so I have another challenge for you. So who had the experience of like growing, putting something, growing bacteria or yeast or something like that in a lab? That like you put things for what's called an overnight. Anybody did that? Okay, I guess a large fraction of people. Those who do not, maybe somebody could, I'll write the question, somebody could describe what do you do when you do this? Just tell the people and I'll write some of the question.
Take some media, take some bacteria from a glycerol stock for minus 80 degrees, put it in the media, and it stays there overnight in a specific temperature, let's say 28 degrees. And when you come in the morning, the concentration of bacteria is very high.
You did it! Okay, so here's the thing, you understood, it's really magic. Before you go home at the end of the day, you just put like a few bacteria inside this media, usually like 5 ml, 10 ml, whatever. You just put it there, you go home, it shakes overnight, you come back in the morning, it's full, meaning like they saturated, they grew to as much as you'll get, and you have things enough to keep you busy for the rest of the day. Okay, now I want to think about what happens there. Like in this, it's called a saturated culture. Doesn't matter. And now the question is, what fraction of the volume is now bacteria? Is it roughly 10%? Oops. 1%? 0.1%? 0.01% or less? Is the question clear? So those who did it, I hope you have some, you must answer. Those who never, passed next to a lab and never had, think about it, from the description that you just got. You put this, let them grow as much as they can, and then you come, it's usually like yellowish something, and the question is, okay, who's voting for A? 10%? 1, 2, 3, 4, 5, 6, 10. Who's voting for B? 1%? At least half. Who's voting for 0.1%? A third. Who's voting for 0.01%? A few. And who's voting for less? Only me. Okay. So, how do we do this? The challenge now for the next 10 minutes is A, if you need to go to the restroom, go to the restroom. B, try to calculate it in some way, or at least come up with an idea of how to calculate it. Those of you who've never played around with growing a culture in the lab, because at least half of here did, more, try to find somebody else and you can interview them, or actually try to solve the problem together. Okay, the challenge is clear. 10 minutes, do what you need to do, and also try to at least either come up with an answer here or come up with a method to do it. Good, so you were given a challenge to try and think how would you come up with a fraction. Any suggestions from the audience? What ideas? Yeah. More ideas? More suggestions? Yes.
Start with the initial concentration and then multiply it by 2 to the power of the rate of multiplication, like the number of times that multiply overnight. Yes.
Good. Okay, so start with number of cells you put, you see something about the division time, and you get something. Good. More suggestions? Yep.
You can estimate by I the volume of bacteria that you add into your culture, and then multiply that by the number of cycles in which you expect it to double, and you can say what your volume of bacteria would be.
Good. Okay, so that's kind of, okay. More ideas, more suggestions? Yep.
You need to think of the stopping condition. what is the opposite force that makes them not multiply?
Which is what? What is the force that stops them from?
We were talking about toxins, like the toxic materials that they.
Good. So it might be something with toxins. Yeah.
I think you also need to consider the concentration of nutrients in the medium itself.
Great. So that could be another stopping condition. Like you put some nutrients, you give them some food, and they're eating the food. So either they're stopping because they finished eating the food, or toxin, or something else. I think usually it stops because of eating the food. Any more suggestions? Okay, so yeah.
I think eating the food should be considered also to, like, it's the other way around. Like the cells are growing and they also consume the food. So it's like both sides. It's not just that it will stop them from growing, like keep growing. It's like you need to consider it in terms of, it's like you have less media.
Okay. Yes. Last time.
Starting volume is probably pretty important to determining the end, like the fraction at the end. Like if you start off with a small volume and you leave it overnight, then they're going to reach a certain maximum much quicker than if you started with a larger volume.
Okay, so the suggestion of how much it depends on the volume. Yes.
I don't think it does depend because we're talking about saturation. So you leave it for as long as you want. I don't know how it relates, but I think maybe OD, optical density, could help in this because you know the OD of when you stop with a saturated culture. So I don't know how it relates. But
Good. So there's different strategies here. I'm thinking. We won't cover all of them, although there's all sorts of interesting relationships how to approach this. I like the suggestion of going for a second with the amount of food that you gave them, like with the nutrients. Anybody remembers anything about how you prepare these things? How much do you put there? How much food is in there? What? Okay, so I think, yeah. Yeah, so I think in bacterial, usually you put something like 0.2% sugar inside, right? It's like 2 grams per liter, something like that, when you grow bacteria. So that's one way to approach it in that direction. And, so if you ever played with it, it would be, if you're putting 2 grams per liter of whatever it is, glucose. What was the
So you can just translate, the glucose is kind of like bacteria. You can say, just translating all the glucose into bacteria.
Okay, that's a pretty right? Like it really simplifies the problem by a lot. Like we could do all of some of the suggestions for here, but like seriously, what you have is like you're turning glucose into bacteria. Then if you started with so this is equal to 0.2%. Right, because a liter is 1,000 grams. You'll say I'm going from volume to weight without blinking. But that's fine because the density of almost everything is 1 in biology. So no need to worry about it so much. So if I have 0.2%, then yeah?
Just one question, like what determines bacteria from stopping multiplying? I assume it would stop before there's no glucose anymore, because then it would just die.
Yeah, so that connects also to the question of like the stopping condition, etc. You could easily say they stop because they have nothing more to eat. It could be toxin, but usually it's not.
I'm saying maybe
they stop before that.
I'm saying they have less to eat.
Yeah, so they're pretty good at eating. So it's true they might stop before it, like there's nothing, but this remaining thing is pretty because it's like you can think about evolutionarily. If your friends, why should I stop if my friends continue? If I do that, I won't get very far in the competition in natural selection, and therefore people. Those bacteria are trying to eat everything. People also. Big problem. Okay, but just a second. So this is like actually simplifies a lot because you have this. It doesn't happen in 100% efficiency, right? You're losing some CO2 and some conversion efficiency, etc. So it's pretty clear that from this, it would be very difficult getting to 10%. I would make the claim that even getting to 1% would require some magic, even though they're turning this, but they're also taking some water. So maybe anyway, it's around this. They would be very inefficient if they stopped here. Okay, so that's one way to approach this. Okay, this, by the way, is okay. So this is one way. There were two other ways. Let me mention them briefly. One was to say, okay, how many cells did we start with? We know the doubling time, and we know when we stopped. All right, that was another suggestion. It came up several times. So how would one do that? You need to know how many bacteria you started with. How many? Yes, that's tough. 1,000, 1,000,000, 1,000,000,000, something like that. Okay, let's say you knew that. Okay, what would be the doubling time? It depends, but let's say 20 minutes, 30 minutes, an hour. But this now, for how long? Let's say 10 hours, 20 hours. You know, this is a logarithmic process, exponential process. A mistake here could be fatal. Like, you know, between 20 minutes and an hour, after you have, you know, very soon you have a difference of 1,000,000 or like 1,000. But also we have a factor of 1,000, whether we start with 1,000 or 1,000,000 or... So there's all sorts of... It's not a robust way to go about it. This is way, way more robust. So that's another... It was a valid suggestion, and I like it, but it's not very easy to get something within a 10-fold error. So just one second. I'm showing you here an example. You saw up till now, I was always like being large. Like, you know, you give me a number, I'll do everything, it would be okay, don't worry about it. Here I'm showing you the counter example. Like it's good to do all of that thing when you have something robust and you know in terms of accuracy that you need, I need a factor of 10, so I don't worry about a factor of 2. But here there's some mechanism that actually would easily give you a factor of 10, a factor of 100, a factor of 1,000 mistake, and then you're in trouble if you want... Okay, so that's the reverse example. Okay, the other suggestion that was here was about going through ODs. That's actually a more, you know, that's a more elegant way to try and approach it. If you know something about the OD that you get, usually you get an OD of, I don't know, like 1. And if you know how many cells are per OD, you can do something. But that requires some numbering. Actually, I like it. It's like 10 to the 9 bacterial cells per OD. You can multiply. It comes up pretty nicely. But it's also not very robust.
What is OD?
OD is optical density. It's like the way if you want to know how many cells there are, you're shining a light. You're looking at how much light you have afterwards. And the more cells you have, the less. It's like proportional. And you can calibrate it. And from that, you just see what's the optical, how much you lost. And then you know how many cells there are.
It will work only for bacteria that has a strong OD signal.
So I think as far as I know, maybe...
bacteria is hard to...
Yeah. Which bacteria?
Sulfitobacter.
Voila. Okay, tell me more about it. Tell me more. It's interesting. I never heard about it. Maybe they have chloroplast, something with like photosynthesis. No? Okay.
Just transparent.
So transparent? Wow, I'm shocked.
They have very high concentration. You can detect the OD, but the low concentration that they usually work with, you cannot see it.
We might put it into the next edition of the book if we ever do one. It's really cool. Okay. Okay, so what I want to tell you, okay, here's like it's interesting to differentiate between robust ways of inferences and less robust ways of inferences. Okay, now let's say if I was asking you, so we're done with that, but if I was asking you these bacteria inside in saturation after they finish growing, okay, their density inside this, how does it compare to other things from real life, from like that you're used to? Let's take an example. Let's say in comparison to the density of students in this class. Is it much higher? Is it roughly the same? Is it much more dilute?
Compared to the room?
Let's say this, students here inside the room versus the bacteria after they grow to saturation. Are the bacteria more dilute than you are?
Yes.
Yes? Okay. It's a new way of voting. Roughly the same. Who says yes? Yeah, I have yes. And much more dense than you are here? I have a few yeses as well. Okay. Maybe you ask them if they could stop this for... Okay, so... What? You're not saturated yet. So I don't have time for that, even though I think it's okay. Like, okay, how would you approach this? Let's say we want to do the calculation. Yeah?
I mean, these are 1 in 1,000, right?
Yeah, 1 in 1,000.
So I just multiply the number of people in 1,000 and we don't get in, I think.
Okay, that's a cool way to say it. You're saying, there's no way I could fit 1,000 times the number of students I have here. Right?
If you just
Okay, so Hadas suggests, it's true, but like we're in a normal class, let's do a yoga class. Right? If it's a yoga class, maybe we could levitate. Okay, so let's check what could make sense. Okay, so what's the weight of the class? How many students do we have? Let's say we have 100. Okay. Now let me be more than tenfold just for a second. Now let's say we have 50 students, weighing each 70 kilograms. Okay, so we have about 3 tons of students here. Okay, 3,000. Okay, what's the size of the class? So how big is this? 10 meters, 20 meters. So let's say 10 meters. How much is this? Let's say another 10 meters. And how high is this? I think it's more than 3. I'd make it 5. 4. You wanted 4. Let's make it 4. Now let's make it so it would be nice. Few. Let's make it 6 just so it would become out nicely. Okay, so how much do I have here? 10 times 10 is 100, 600. 600 meter cubed. No, 60. 600, yes, 600, good. Okay, so now 3 tons. How much is it in, how much cubic meter of students do we have?
3.
Yeah, so it's about 3 cubic meter.
Why are we converting it to?
Just because I have this in cubic meters. So I'm just doing, because this is like fraction.
Yeah, but the fraction you did here was in mass to...
Yeah, mass to mass, volume to volume. Yeah. It's all like, again, everything is like same density as water in life, in biology. Okay, so I have what's the fraction? It's like 3 divided by 600. Which is what? 0.5%? Okay, so indeed, kind of like the bacteria are more dilute, as you suggested, but not by, crazy much. So like this suggests we could fit not 1,000 times more, but like a lot more students here. We could open the course and we could have, how much? 500 times more students? We could, it's kind of, like we could fit, it's pretty, like all the students at Weizmann, if we were able to do a yoga class of levitating. That, by the way, also suggests something about like in our intuition, like you don't believe me, right? There's no way we could fit so many students here. That's also, but we just came up with, a calculation that shows it. So what's happening here?
You want your students to be alive and comfortable?
Yeah, so we have already preconception of what is reasonable. And we don't have a great intuition, somebody was saying.
So are we organized in space?
Yeah, exactly. So there's something in this thing with space that, like, 3-dimensional, 1-dimensional, 2-dimensional, it does different things in different dimensions. Okay? Good. So let's move to that. Eraser somewhere. Don't know what I did with it. Anybody remembers? There's an eraser here. Okay. So you got this. We could invite more people to the class. Now let's do the following experiment. I think we're making good progress here. Let's keep in this effort of trying to check our intuition and developing our intuition about sizes and numbers. So let's say we do the following. If all of humanity holds hands, so I'm inviting them all here to Weizmann, and they're holding hands one after the other. How far can they reach? Let's give us a few options. 1, A, they could get to Sinai and get to Sharm el-Sheikh, which is where we have the COP now, dealing with climate change. B, they would reach Antarctica. C, they reach the moon. Or D, moon and back many times. Okay, is the question clear? We invited everybody to this to a big party. We're telling them hold hands one after the other, like in a line. And the question is how far would it reach? Okay, one place they might want to reach is to the COP 27, dealing with climate change. Another is to get to Antarctica, then to the moon, or to the moon and back, and moon and back, and moon and back. Question is clear? Okay, who's voting to go to Sinai, to Sharm? One. Okay.
At least three.
Who's voting? Who's voting that they'll get to Antarctica this way? I have a few. Who think they would get to the moon? Most, I would say, half. And moon and back many times. Okay, the other half. Great. You like the question? You have an answer? How do we do the answer?
Length, like wingspan, times the number of people.
Okay, so we have about how many people?
8 billion.
Okay, so actually somebody was telling me yesterday that yesterday was the day that we passed 8 billion, right? What do you think? So that like yesterday was the day when there's 8 billion people on Earth. What do you think about it? Okay, so on the one hand, first of all, I think it's good to mark that like in our mental memory because like it increases so rapidly. We should be aware of it. It has so many different implications for us in so many different ways, so we should be aware of it. At the same time, we shouldn't take it. We should just be aware that nobody knows exactly how many people there are on Earth. Right? I think the Yinon Baron from my lab was trying to get at the uncertainty on this, and if I remember correctly, it was 100 million. So no, so I think so. You know, in other things could have been a billion, but I think the claim is that it's known to about 100 million. Anyway, that again shows you something about accuracy. So, you know, humanity, we know pretty much about ourselves, but we're still uncertain to how much, in terms of percent.
Percent of what?
Percent of humanity. To plus minus, we have X number of people, plus minus how much?
1%.
So if it's 100 million out of 10 billion, 8 billion, so that's 1%, which is nice. You see, even on humanity, for which we know everybody has Facebook or whatever, like we have a lot of information on people, right? That's what, you know, we're really good at knowing. We know plus minus 1%. Okay, that's pretty good. Many other things, it depends. Okay, we'll see. Anyway, so 8 times 10 to the 9 times how long would, you know, it would be about 2 meters, right? Something like that. So it's about 16 times 10 to the 9 meters, which is 16 times 10 to the 6 kilometers. Okay, I'm 10 to the 3. So I have about 20 million kilometers. Okay, so let's make it quick. Let's say this is the Earth. Israel, Sharm, how much is this?
1,000 kilometers?
Yeah, about 1,000 kilometers. Okay, Antarctica, how much is this? 10 to the 4 kilometers. This is the moon. How much is, not to scale, how much is this?
400,000 kilometers?
Yeah, so I think 300,000 kilometers. If I have 20 million, I could go back and forth like 50 times or something like that. But you know, it's okay, so well done to, I think you also understand now intuitively, maybe a bit further. I think there's several notions to understand here. One is, there's really a lot of us, right? Which is also shows you, I think, it's something positive about the potential. Like if we really work together on some problem, I think we don't really have a good intuition what we could achieve. Because like seriously, we could go, you know, if we're holding hands, doing something together, we could reach the moon and back 50 times. It's like, it just shows you there's really, like we don't have a good intuition to how many people we have here and what we could achieve together. I think it also shows something about the challenge of, you know, feeding all of those people, doing all of that stuff. When I was thinking about this problem, I actually wanted to give you another option, right? Not just, I don't like many times. What does this mean, many times? So I wanted to suggest, that we'll go somewhere else. But what?
Mars?
Yeah, so actually the sun is too far. Mars is also too far. Venus is too far. Actually, I couldn't find anything interesting to go to. So we really don't have nowhere to go. It's really, there's even in the time of the year when Mars or Venus are the closest, it's still more than 50 times the distance to the moon. So I think it's also an interesting perspective to think about we have Earth. If we really make a crazy thing, we could reach hands and reach to the moon, but actually there's nothing waiting for us in the moon, seriously. Even it's actually not even a lot in terms of area or whatever. And anything beyond that, it's way further than reaching the moon, and the moon is tough. Okay, I think you got the notion of what I'm so we did that. Let's switch, change for a second to something else. I want to give you more about perspective. This was about, global things. We want to go down now into the cell and saying the molecular components. And this is something that is challenging. Why is it tough?
We have no intuition.
Yeah, so because it is small, and because it is small beyond any smallness that we're aware of, we don't have good intuition. I think you already understood. That's why I'm advocating that numbers could give us insight into that. But let's develop that insight. So let's do a quick exercise of developing insight into those molecular things. Okay, so I'll show you several things, mostly from the book that Rob Phillips wrote. We wrote together, and many of the illustrations are mostly from Nigel Orme, this very talented British illustrator, and David Goodsell helped us also with some things. You might have seen some of his works before. How do I move slides? Good. Okay, so you can put things on a scale. Okay, scales are pretty nice, but this scale is special. What is special about it? Right, so we're putting on a log scale, meaning the distance is the same as the fold change. And as you can see, it's 5 orders of magnitude. Each such line is an order of magnitude. And what do we have here? We could start from, this. What do we have here? We have molecules. What are the size of molecules? Yeah, so it's about a nanometer. Or if you remember, an atom is this thing called angstrom. Angstrom is a 0.1 nanometer. Nano is 10 to the minus 9. And molecules are usually on the order of 10 to the minus 9, 1 nanometer. Okay, so when you think about molecules, if you remember, nanometers is, I'm trying to condense what you need to know. Nanometer, if you remember that, you're okay. Okay, now we're moving from molecule into complex molecules, like proteins, ribosome. You go in order of magnitude higher. But these things, the crazy machines, these things, how come we only went 1 order of magnitude? Yeah, it's this thing with the volume, 3D versus 1D, as we talked before. Because it's not like the molecules, to make a protein, they don't just make like a spaghetti. They make a shape, and that means you can condense a lot. If it's a factor of 10 in linear distance, it's a factor of 1,000 in volume. Good. And now you can go to viruses, another order of magnitude. You can go to bacteria, another order of magnitude, and you can go to mammalian cells, another order of magnitude. Each such order of magnitude gives a factor of 1,000 in terms of what you can fit in. Okay? So that's kind of all you need to know. 1 nanometer, not only, but 1 nanometer, 10 nanometer, 100 nanometer, 1 micron, 10 microns. Make sense? Okay, it's a lot of information that I'll show you, but I think it will help. Okay, let's go from here onwards. Okay, so let's make a quick puzzle here. Okay, what do we see here, and what are the sizes? So so you can see there's a color code here for the atoms. So for example, you see this is oxygen. What is this?
Water.
Okay, so you see 2 oxygens and something in the middle. CO2 sounds like a good guess. What is this? Water. Okay, you already have the oxygen and 2 stuff. Water. Okay. What could this be?
Phosphorus.
Yeah, so the first thing that got me excited about biology is I remember I was doing my undergrad in physics, and a fellow, Danny Glick, a friend of mine, was telling me, listen, I was reading this in Scientific American, this amazing thing about how, how are cells built? How is how do you make like walls or something between something alive and the other stuff? And it turns out you just throw in something and it builds it by itself. This something is this stuff, lipids or phospholipids, fats if you want, that they create the gates for our cells by themselves. Okay, so this is what it is. What is this? Probably. Okay, and now, there's the names for this, but I'm asking you, I'm curious about this. What is this? It's always important to put a scale if you're showing something, to understand, if you're showing size of something. So what will be the scale here? Okay, few nanometers, good. Because you remember, an atom is like a nanometer, so this is...
No, an atom is an angstrom.
What?
Atom is angstrom.
So, right, atom is an angstrom. Atom is an angstrom. Atom is an angstrom. Yeah, but this is like hydrogen atom, which is pretty small. This, weighs 30 daltons, so it's already quite a few. More towards a nanometer. What?
The atoms are not compact, right? If you have like
no, no. So it's like per dalton, it's like roughly the same. So it's true that the atom is a nanometer, but that's like an angstrom. But that's like the hydrogen. When you have something bigger, it's a few angstroms, and then a few angstroms. But then now you're putting a few of those few, and then you're getting roughly to have something like 1 nanometer to a few nanometers in scale. Okay, you remember the mRNA versus protein? Here's a depiction of it in a visual manner. Okay, this is myoglobin, something that, kind of like our hemoglobin that, that transports oxygen. And here's the mRNA that codes for it. How cool is that? Right? Now this might, be more wrapped or less, but I think now you see this David and Goliath or whatever you want. This is like a real depiction of real. This is like, into to scale. Okay, what would be the scale here? Okay, 10 few nanometers, something like that, right? 5 nanometers. Okay, you got it right. But I hope this will be etched in your memory. Okay, now you can look at all sorts of different machines. So what do we have here? We have like all sorts of proteins like insulin, trypsin, whatever. ATP synthase, the thing that builds ATP. What is this?
Sugar.
Yeah, so we might remember it from before. Also, you see something. Also, you might see something here. It is like the berry. This I think is this. So this is sugar, as far as I remember, like glucose. And those of you, that studied that, I think like you're supposed to have either like a small aha moment, because like very often people talk about like sugar and hexose kinase, all sorts of things that do stuff on sugars. And it's not really clear what's happening here. Like we don't have like a really mental picture of this. So this is how it looks. It's like this huge thing that like holds this, minute. Okay, and this is it. Am I right?
So why does it have to be so big?
What? Okay, so I think this brings an interesting question. Why does it have to be so big? I don't suggest to have an answer. And also, I don't think we have time for an answer, but I think it's a great question. Okay, which I think shows one of the things that I want to emphasize in this course is that by being qualitative, it brings new questions to the table that you wouldn't ask otherwise, and with new questions that they're also pretty deep questions usually, you can go pretty far. Okay, anything else that you like here? Okay, let's move on. Okay, so you have the scale. This is now 10 nanometer. Okay, we will talk about this is a distribution of the length of proteins. How many amino acids are in a protein? Okay, and you can see the histogram, the distribution. What do you think the numbers here are? Like, what's the characteristic?
100.
Okay, a few hundred. That's true, a few hundreds of amino acids. What do we have here? This is all sorts of things related to gene expression. You probably heard about, maybe you heard about some of them. What is this? Yeah, so you can see the ribosome, and you can see, again, we're in the scale of about 10 nanometers. Here they are, just focusing on them. You can see the ribosomes, both for the prokaryotic, the bacteria, and for the eukaryotic, like us. And you can see the thing that builds, the thing that gives them the mRNA, the polymerase. And I think there's also things, cool things here, like how similar they are. It's like billions of years of evolution distance, and they still kind of look the same, even though probably Ada Yonat would have a different perspective because everything matters here. But and you can also see something else that's interesting, right? You remember what we found about the so the mRNA, we just is way bigger than the amino acid, but the thing that makes the mRNA, that's the thing that makes the protein, that goes in the reverse direction in terms of sizes. I don't have something smart to say about it.
Just tells us that our intuition is not so.
Yeah, maybe that shows again how not everything that we're used to from normal life has to happen the same way inside cells. Why? Because it's a different world out there. It's a different different constraints, different selection. Okay, there's a lot more to do here. I don't know. Okay, this is just going back to this thing of like the gates, the bilayers. So how big is this membrane? Like these are membranes. How big are they?
10 nanometers,
1 nanometer.
So we said if we have a molecule like that would be like 1 nanometer. Now we have two of them, but they have this a bit of a long tails. So a few nanometers. Let's see if I'm right. Yes. Okay, you can see things stuck inside the membrane. What are they? Yeah, so it's again proteins. But again, you can see now this thing that was mentioned before. They work in these oligomers. Like there's a few copies of them that come together to do work. And so what would be the scale here? Yeah, so we already know this would be a few. This is a bit more. And these machines, when they come together, they're on the scale of 10 nanometers of a few proteins. Here you can see this oligomerization state in many examples. So you can see, dimer, trimer, octamer, tetramer, all of those, I think it's Latin names of the different number of components. You can see like it repeats itself in all sorts of different ways. You can also build like really long ones if you put in a linear scale. That was also came up previously in class. So you can see here the major components like collagen, microtubules, etc. Anybody knows what this one at the bottom is?
The motor protein.
Actin and myosin. Which one do you think this is? Exactly. Okay, and you can see here again this 10 nanometer. Now they're much bigger than this. Why? Because they're like really long oligomers of these components. Okay, that was, we did it about the stationary phase. So if anybody wants to know, this is the yellowish stuff of the way they look. What would be the size here? If this is to scale, the bacteria? Yeah, so that's about 1-2 microns. This is the hindgut of a termite. Okay, like they're also doing this thing of putting cells in saturation. But you can see this is pretty dense. right? Because they're kind of like doing the experiment we're thinking about adding, many more students to the class in 3D. And the way they do it is they give much more than this 0.2% of glucose. They're doing this, I think it's called batch fed or whatever, like continuous, whatever. Like they're giving it more and more things to eat, and then you have the feeding off of some grass, and then the bacteria. So what would be the scale here?
10 micrometer.
So each one of those would be like one micron like this, or say a few microns like this, and there's few here. So about 10 microns. Now we could go to a virus. What you see here, I think, is a nice picture. It's a virus. It's a bacteria filled with viruses just before it's about to explode or just get emitted. So you see the nascent viruses as they're going to come out. So what would be the scale here?
1.5 micrometer.
Okay, so we said it's about 1 micron for, that's usually like this part of the bacteria. So this is about micron. You can see inside how much would the viral be? About 0.1. Okay, 1 micron versus 0.1 micron. 1/10, which is 100 nanometers. Okay, you can see there's lots of bacteria. So I knew about all of these, but I never knew about the one that doesn't have OD, so I want to hear more about it. But you can see all sorts of variety of that. You can see other types of cells. Okay, so we talked about bacteria. You can see it here as a scale. What is this? It looks like an egg, but it's actually, it's the type of, I don't know, some mammalian cell that have the nucleus and they're spreading on the surface. The question now would be, I don't have a scale here. Strange. Yeah, so this could be like a HeLa cell, what you saw there. And okay, now the final point. You remember we did this thing with the logarithmic scale. So here's something from a former student. So after you finish the course, I hope you'll find it useful in different ways. If you do, please shoot me an email. Also during the semester or something, if you use it in some way, I know you're quarreling with somebody or you have some bet with your family or something like that, let me know. So here's one example. It's from a friend of mine who was also a student here, Shai, who said, I'll read it in English. Okay, listen to a funny story about your course. I was hiking in Vermont, and next to the parliament, they put this big, what is it called, pumpkin? Pumpkin, and we're saying we'll give a prize to those who get the best answer. Like, how much does it weigh? So I went to the Facebook page of this contest, and there were already 200 previous people who put the guesses. So just for the fun of it, Yafit, which is his wife, she read to me the first 40 guesses, and I just put it in Excel, and I did a geometric mean like we learned in the course, and I put that as my best bet. Okay, and so this is his daughter, and I think this was his guess. Anybody wants to guess? We don't have a lot of time, so just, How much do you think?
300 kilograms.
Okay, so I think they work in pounds. I don't know why. So anything you say in kilograms multiplied by 2, or anything you say in tons, what is it?
1 ton is
600 pounds.
So 600 pounds are here. 700, 1,000, 500. Okay. So he did that, or she did it actually. She did it based on, and she got 1,139 pounds as the guess that he gave based on those on the Facebook page. And so they just announced the results. When he was sending that, it was 1,138.
What was the price?
Did they win?
So I don't know exactly what was the price, and I'm not saying that I don't give you a guarantee that it would work so nicely. But this is like, so he got 0.1% mistake, and I think it was nice that he actually made also he wasn't saying, it's great. He just, he said, okay, it's like 0.1% mistake. I think that's showing us it's really the right perspective on how accurate, one could be and what can we achieve. Good, I think we did that. Let me give you, we still have, now it's an H plus teaser. What does that mean? So the final question to keep in mind, and I remind you, so what you need to do next is to open and find the next exercise, and if you have any problem, let us know. So, in a bacterial cell, you see we're doing a lot of things for bacteria just because they're like nice and fluffy and like there's not a lot of variation. You could think about like an E. coli and work with that, but then you can infer for all sorts of other stuff. In the bacterial cells, how many H plus ions are there? What is H plus? It's also called the hydronium, I think. And it sometimes looks as a H3O plus because it, it jumps on a water molecule. But it's like a very basic thing, in many stuff. And so the question is, how many are there inside this bacterial cell? How big is a bacteria? 1 micron, you know that. Okay, so is it about 10 to the 2, or 10 to the 5, or 10 to the 8, or 10 to the 11? Okay, as you see, I'm not trying to לתפוס אתכם בקטנות, as they say, like to ask you about, I'm giving you quite a range. The question is clear? Okay, who's voting for 10 to the 2? 1, 2. Who's voting for 5? Now it would be nice if it's 5. It's actually 8. Who's voting for 10 to the 8? Seems like more than half. Who's voting for the 10 to the 11? Another quarter. Okay, so you remember this? Good. So the next lecture would be about concentrations, trying to develop our intuition there. And this would be the kind of stuff and what you learn from it. תודה רבה.